Thanks everyone for joining us. So today I'm going to talk about data management and file systems on Expanse. Uh, and this is part of the ongoing series. And I'm pulling a lot of content from Manu's Expanse webinar from before. So some of you might have seen that. Let me see if I can go to the next slide. Okay, yeah, that looks good. So just a quick overview. I'll start with an example workflow, just so you know the sort of things someone might do with file management on a system, and then look into data management, why we need that, the tools that we have, and then dive into the file systems on Expanse, because we as you go along this course and start running things on Expanse, we want to be careful about where we run things and also know the capabilities of the file system. So hopefully I can give you a good overview today. Specifically, I'll talk about the Lustre parallel file system and its architecture, and then quickly go over a few example scenarios where you can make decisions on where to run, and also give you an example of what happens if you do the wrong thing. So hopefully with that, we can summarize the talk. So an example workflow, and this is, I think Manu had picked one of a real workflow that he had worked with. But it could start with a simple thing as moving your code to your home directory. And you can do that using SCP, for example. If the source code is small, that should be easy to do. Or if you have a Git repo, you might do a pull right on the system directly. So all kinds of options to get your code in there, and then SSH to the node and compile. And then you could have lots of steps in your workflow. So you could have a pre-processing step, for example. So in this particular example, they were moving files using rsync from a client to the project space on Expanse. But you could use Globus, for example, to do the same kind of thing. And then the files that they have were big tar files, and then there was a step to do some splitting of these files to fit into a local SSD, and then do some main processing steps to copy these files from the project space to the local SSD, do your classifications and runs, and then take the output files and push them out to the external storage. So all these steps could involve different file systems. For example, the project space is a large parallel Lustre file system. The local SSD on Expanse, it's NVMe storage. So, and also the Expanse nodes can connect out directly. So you could technically rsync out even from your compute node as part of your job itself, if you want to push to external storage or pull in data directly into the compute nodes local scratch, both of which are things that people do. But those are just scenarios. So what is data management? Basically managing data before and after computation. That's one piece. Like you have data collections that you might have to copy or sync. Managing data during computation, you might stage some of this data into local scratch and do something there, and or generate data during a simulation. All along, the data provenance and integrity is important. So you should have checks for those. And the data sources could be numerous, right? You could have external sources like sensor data or camera data, satellite images, or simulation data from elsewhere or from on Expanse. And there's all kinds of storage mechanisms. External hard drives on a remote machine, hard drives on a local machine, on a supercomputer, local, home, parallel file system, lots of different options. And it's important to manage the movement of data in and out, and also writing out simulation data in a good way, because the performance and scalability of your application might depend on this. And with I/O, there comes additional responsibility. Like if you're running on a Lustre parallel file system, when you do the wrong thing, it not only affects your code's performance and scalability, it affects the rest of the system and everyone else on the system. So it's critical that you understand how each of these file systems work and what they're good for. And that's hopefully my talk today can give you some background on that. Let me see. I see some things in the chat. Okay, not much there to follow up right now. Okay, so and there are tools for moving data in and out. I mentioned Globus. It's a tool that provides fast and secure and reliable file transfer and data sharing mechanisms. Expanse has an endpoint, and you can access Globus from the web interface and initiate your transfers from there. One good thing about Globus is there are options to do checksumming, so you can be sure of your data integrity, for example, after your move. And also it retries if there's a problem, which can happen sometimes. For example, you might have a file system issue and something gets hung up. It will retry automatically. So it's a good tool to have. And you can use Globus Connect Personal to make your own machine into an endpoint, personal endpoint. So technically, if you're trying to move data from your laptop or your desktop over to Expanse, one side of it would be this Globus Connect Personal that's on your machine. And then the Expanse side of it is the Exceed endpoint for Expanse. So, and then it's a point and click interface. And if you go to globus.org, you should be able to look at that. There are command line interfaces also. And one good thing with Globus is you can authenticate with your Exceed credentials there. And there's a lot of useful information related to data management on the Exceed portal. So you should take a look at that link when you have a chance. Now, there are simpler tools, of course. You can use SCP, SFTP for like small files. And if you do a man on SCP or SFTP, you can get all the options there. You can also use things like FileZilla or other transfer tools that you're comfortable with. We also have tools like Aspera installed on our data mover node. So if you need some specific mechanisms to move, you can do that from the data mover node. And you can use rsync, of course. Also at SDSC, we have a couple of really cool projects which provide you with a lot of additional tools. And so I'll start with Open Science Chain, which basically utilizes blockchain technologies to provide like traceability of research data. So if you're sharing data among different research groups, you want to be able to verify the data sets are correct, the ones that you're using, or you can basically ensure the integrity and also check the provenance of the data that you're using. And also it's, if say you have published research and you have data stored here, it's possible to quickly verify for both other people in your research group and other research groups that, oh, this is the exact data set that was used for a particular published research. So that's a nice project that is enabling this. And basically it keeps a cryptographic hash of data sets and metadata information. And you can interact using a Open Science Chain portal, and I have a little bit of a snapshot on the right. And you have the ability to search, verify, validate research artifacts that are contributed by both your group and other research groups. And you can create a workflow linking multiple sources of data. And you can interact directly with from Expanse using a Python API if you need to. So it's a neat thing to have. And if you need more information, the contact information for Open Science Chain is on the right, and Sivagnanam can help you with that, and her email is there too. There's also HPC Share, which is based on Sydney Lab software that lets you share data and videos, basically collaborate among researchers and share data and comments on any file or folder. You can upload files from Expanse or from elsewhere. And you can do this via command line, API, or browser. And you can annotate this data with rich text and create visualizations of tabular data. So it's pretty nice tool to have. You can check that out at hpcshare.sdsc.edu. So that was a pretty quick overview of all the data management aspects. So the question was, are these data transfer services free? I think so. You can double check, but I believe they're free. If anyone from SDSC is on and has any comments, you can drop it in there. But these are all good things to keep in mind when you're doing all the data management tasks. Now that's all getting data in and out of Expanse, and keeping track of some of the integrity and provenance of the data and so on. So you have all these tools, but when you're running on Expanse, mainly you're interacting with the file systems. So I'll spend the rest of the talk talking about the file system options on Expanse. I mean, that's a place to store data and files and manage data. And you could have computations with thousands of files or hundreds of thousands of files, or in some people have millions of files. And some, especially during temporary files during simulations, could be very large in number. And you could have large shared files too, like if you have a large parallel job, like a weather forecasting job, you might have large checkpoint files from each process, or like a large file for the combined run. Or you could have, long-running machine learning jobs where you're checkpointing, or a lot of HPC codes do checkpointing too. So just a quick overview of Expanse, and I think Mary probably will go into it also, so I'm not going to spend too much time, but basically we have 720, actually this has increased now because of the extra industrial rack, but we have 700 plus AMD EPYC 7742 compute nodes. These have 128 cores per node. The key from a file system perspective is the 1 terabyte of NVMe per node. And also on the storage side, we have the 12 petabytes of Lustre file system. This is raw. I think a little bit less available space, but it's a pretty large parallel file system that's broken up into 2 spaces, and I'm going to talk about the Scratch and Projects parts. There's also a Ceph file system that has now been mounted. It's not yet fully available for all users, but it's coming very soon. And we have a 1 petabyte home file system that looks like a lot, but we have tens of thousands of users. So I'll talk about the quotas, but it's quite limited on the home file system. So you can think of Expanse's storage setup as a tiered storage setup. You have the node local NVMe drives for workloads that don't need to share data files across nodes. Now, a lot of our users run single node jobs, in which case You could stick all your data for your code in the node local NVMe drives. So you don't need to even think about data going across nodes because you're on a single node. But also, there are a lot of parallel jobs where each task might write out a lot of temporary files during the run. And that can also go to the node local NVMe because like the data from task one is not needed by another task. So you could be doing that. But of course, there are cases where you do need to know the data. You need to have the full picture of the data. So that's where you would use a Lustre file system for large capacity of shared storage. It's Lustre, and I'm going to go over some of the details of the architecture. It's good for certain kinds of workloads and specifically like a high bandwidth and large block IO. And I can talk about that a little bit more when we go into Lustre file system details. And then there is a NFS for user home directory storage. The Ceph object store would be for short-time archival storage and also staging data transfers to cloud-based storage. As I mentioned, it's coming soon. So why do we have all these different file systems? Well, there's the performance access, there's the shared access across nodes. There are the different kinds of, I hesitate to call it backup. It's probably like a short-term was long-term storage and like storage for like the project level. So like usually our allocations are for a year. So that's what I would consider long-term. Definitely do not think of any of these file systems as the place to put your critical data. It's meant for mainly simulations that are ongoing or something that you need for the duration of a project. It's not meant to be an archive where there are no backups for the large file systems, for example. And we do have quotas, and I'm going to go over that a little bit later. So applications, of course, depending on what kind of IO you're doing, and the performance you need, you can choose the file systems. I think here there's an example of an IOR benchmark, and I'll go into this also a little bit detail, but you can kind of see, you can do a file per process example, for example, so which will tell you the performance of the file system. It also gives you output regarding the file system it's running on. So you can see that's the Lustre file system, and that's the node local NVMe. And the different kinds of bandwidths you get depending on what you're doing. So the storage choices should be driven by what an application needs. Don't just use what's available and or blindly write to like a shared location because it's there. Because sometimes what you do might not be scalable. So the applications really need to adapt when you start scaling up. And by scaling up, I don't mean the like a particular application running at large scale in a single instance. It could be you're running thousands of these applications at a given time because Expanse has nearly 100,000 cores. So it's possible that you could be running 1,000 instances of a single core job. And sometimes that is worse than having a single job that's using 1,000 cores but has a well-defined IO. So it really needs to be keeping that in mind. So a lot of times what we see is people have codes that they developed on a laptop or a desktop, and it writes out 15 files or 20 files continuously, which is fine on an NFS server or even on a local disk. It's totally fine. And even on Lustre, it'll be fine if you run one of these jobs. But now if you run 1,000 of these jobs or like 5,000 of these jobs, you're certainly writing to 10,000 files continuously. That's going to cause a problem. So that's where you have to think about where you are writing. Now, if you write these kind of small file kind of patterns to local disk on each node, that scales beautifully, right? Because each node's storage is independent of every other node. So you're not going to impact globally. And also the NVMEs are kind of geared towards this kind of small file IO. So they do much better. So when you log in, you land on the home directory. It's NFS, Network File System Storage, as I mentioned. Typically, we want users to use this location to store source codes and important files. Don't put large output data in this location. We do have a pretty low storage limit here, so 100 gigabytes. So you really can't hit it with too much IO, but keep that in mind. This is backed up in the sense we have snapshots. So, again, anything critical, my suggestion for users is to have offsite copies, multiple copies if possible, because yes, these file systems have redundancies and have snapshots, but things can go wrong. And if you run on an HPC systems or HPC in the HPC world long enough, you're going to have data loss at some point. So you should plan for issues like that and definitely have offsite copies of anything critical. We've seen cases where people have put like their only copy of their working source code in a Scratch directory. That's a big no-no. So always have copies. Talking of Scratch, so the Lustre Scratch location is in a /expanse Lustre Scratch, and under your username, and there's a temp project directory. And we deliberately named this with a temp_project so that psychologically people realize that it's temporary storage and not something that you should leave sitting there. This is typically where you would put your input and output files, large files. This, as I mentioned, allows for distributed access across all the nodes, so it's a good thing. I think there's a typo here. This should be around 10 terabytes. The storage limit, usually by default, that's what we do for Scratch. Now, that doesn't mean that you go put 10 terabytes there and leave it there. Like if everyone does that, we wouldn't have the space to do it. So just treat it as Scratch space that expands to around that level that helps you run large simulations, but do not think of it as parking space for 10 terabytes. That's not a sustainable thing. And we do have a 90-day purge period on these locations, and this is based on create time. So don't touch files; it's not going to help you. And more critically, there are no backups for these locations. As I mentioned, it's almost 12 petabytes of storage, so it's next to impossible to back up that level of storage. So you can assume that anything on there is basically single copy. If you accidentally delete it, it's gone. If we have hardware issues, then there's possibility. Now we do have a lot of redundancy, so I don't want to scare people. It's basically it takes quite a bit of hardware failure to lose data, but there is always a possibility. So again, if it's critical data, keep offsite copies. We also have the Expanse Lustre Projects directory. This is a location for every group. It's allocated storage. So if you have exceed allocations, typically by default, you get 500 gigabytes for the group. And if a group needs more, like for example, if you're running weather codes and yeah, I know my group will need around 20 terabytes, you need to put that in your proposal and request that, and it will be evaluated. And if the reviewers feel like, oh yeah, that makes sense, weather codes create lots of data and they need this much for processing, or etc., and they say, oh yeah, 20 terabytes is okay, then it gets approved. And once it's approved, you can use this location for that amount of space. This is mainly meant for project-specific data that you need for the duration of a project. So for example, if you have a reference data set that every simulation of yours uses, you don't want to put it in Scratch because it's going to get purged in 90 days. So you would put it in this kind of location because it can stay longer. Or say you have a workflow where you need to run hundreds of simulations, take all their output and then post-process them together. That is, you need all of that output to be there before you can post-process. So then it's another use case for putting data in this location. This is not purged, but if your allocation ends and you don't have a renewal, then we give you 90 days to get the data off the system. So it's not forever. It still needs to be taken off, but it's a longer duration, basically. So think of it as data that you can keep around for a year. But again, this is not backed up. So make sure you have offsite copies of anything important. Now, underlying file system for both the Expanse, Lustre Scratch, and projects is the same one. So this combined actually in the same file system. We just have different policies in the different locations. So then we go on to the node local storage. This is a location that is only created when your job is running on a node. You cannot see this on the login node. This is only on the local. It's local to each compute node. And when your job starts, this location is created and made writable by your username. So it's /scratch, your username, and then job underscore the job ID, basically. And this location is, oops, shouldn't hit and show there. Is node local, as I mentioned. You can use lots of, you can store lots of small files here if you want. Like, so if you have a workflow that's creating thousands of small files during the run, perfect place for it. Its limits are dependent on which node you're on. If you're on compute or shared partition nodes, it's 1 terabyte. On the GPU nodes, we have 1.6 terabytes, and on the large shared, we have 3.2 terabytes. The key is that this location is purged after a job ends. So if you're going to use this in your scripts, make sure you copy out. In your script, you have something that copies out the data. Once your job finishes, it's not accessible and it's purged. So, so we can't help you either. Like even if we want to, the data will be gone, basically. So you need to have that in your workflow. And I have the example demo that shows you example of how to do this. So just to summarize, basically, you have the home directory with the NFS storage, 100 gigabytes limited number of snapshots. Think of it as around a month of snapshots. We have Lustre Scratch and projects. They're both parallel Lustre file systems and have no backups. And then we have the node local NVMe based storage. In terms of usage guidelines, again, I want to summarize the usage guidelines. Basically, the Lustre Scratch storage meant for storing data required for active simulations. Now, it doesn't mean that it's going to be purged as soon as the simulation ends, but it's meant for active simulations. That is, like if you have, sometimes the same simulation might need several restarts and you can leave that data there. So that is okay, but it's not backed up. And definitely don't think of it as a long-term parking space. It has a 90-day purge policy, and it's good for large block scalable IO. And I'm going to talk about what I mean by blocks and things when we go into the Lustre file system details. Then we have the node local NVMe. These are good for metadata intensive jobs, high IOPS. So like if you have file per core type IO with continuous writes, this is a good place, purged at the end of the job. And then the Lustre project space that I talked about. And the last thing I have there is home directories. And as I noted, use it only for like source files, libraries, binaries, and so on. do not use this for IO intensive jobs, especially don't use it for jobs that are scaling up to lots of cores, like thousands of cores, because the NFS file system cannot handle that and it's going to cause problems, not just for you, but for everyone else. So in terms of the order of magnitude of the files, basically, think of the local hard drives, local NVMe are in the thousands of files range. The RAMFS, you can use tens of thousands. RAMFS is memory, basically. The NFS, you have hundreds of files in a directory, it'll be okay. Lustre's, hundreds is probably too conservative. I think you can do thousands of files, but don't do like 1 million files in a directory. That can cause problems. And file sizes, the largest ones can go in Lustre, and then everything else should be smaller. The bandwidth varies depending on each of these locations. So you could get a few gigabytes per second out of the NVMe. NFS is pretty slow. 100 is, again, very conservative. These are order of magnitudes. So you can probably get 200-300, but that's about it. And then the Lustre, our Lustre file system, you can scale out to order 100 gigabytes per second. That's at the top end if you do everything right. So the local file systems are good for small and temporary, and the parallel file systems are good for the large bandwidth kind of things. So this is when I should basically go into talking about the Lustre file system, kind of the architecture, so you know how things are laid out, and then we can also talk about the do's and don'ts of using Lustre file system. So the Lustre file system will have typically a metadata server and a metadata target, and I'm going to talk about Expanse specifically a bit later because we have more options there. And then typically it's connected using a high-speed interconnect. Usually it's InfiniBand or high-speed Ethernet, but typically it's InfiniBand. To Lustre clients, which are the compute nodes and the GPU nodes that I was talking about. But there are also storage servers that are part of the Lustre file system that the metadata servers basically manage how the data lands there. And on each of the servers, there are storage targets. And each storage target itself is comprised of a lot of disks. And that's where the redundancy is usually at the target level. Within a target, that is. So let me take a quick look at the checkpoint. Does checkpoint restart store? Sure. So it depends on your mechanism for checkpoint restarts. So the question was basically, does the checkpoint restart store application state in one big shared file, or does each process save data? And can it overwhelm the parallel file system? So for the first question, it really depends on your application. We've seen both kinds. And it's okay to do a file per core at reasonable scales. Also, like when you're doing large parallel files, shared kind of files, you can manage how it's written out using the parallel IO options so that it doesn't write them out into from all cores at once, and you have some sort of aggregation before you write out so that you're writing from fewer writers. So can it overwhelm the file system? Yes, if you do the wrong thing, right? So I can give you examples. So if you're fluid dynamics people, you've probably heard of the code OpenFOAM. So there, the checkpoint files are essentially at a per, so it's not only file per core, but they also have a file per variable in one of the configurations. Now that sort of thing, you can see how it can get out of hand, right? Like you're running OpenFOAM with 1,000 cores, and then you're running it with 7 variables or 8 variables. Like you know, you'll have at least 5, like the velocities and the pressure and so on. So that quickly becomes 5,000 files. And now, because they broke it up at that level, you can also have much smaller files. So you would have each file being a few kilobytes. So what happens when you write that kind of thing is, and if you make a mistake and write out too often, like if you're checkpointing every few seconds, that can cause a problem. So you definitely need to be careful about how often you write. You shouldn't check. I mean, I would say if you have a 24-hour job, maybe checkpoint every 6 hours or so. Don't try to checkpoint too often. And unless your checkpoint takes a long time, then you can adjust based on that. Also, how you checkpoint, you can do one large shared file as long as you use like an IO library that has some control of how it's written out. Or if you do file per core, you can be careful and not have all the cores write at the same time. You can block them so that only 16 of them are writing at a time, for example. So with these Lustre parallel file systems, it's good to not overwhelm the metadata server with lots of requests. It's better to control that piece. The scaling comes from the storage servers. So I'll talk about the Expanse one and kind of explain it. So this is kind of the typical Lustre file system with the clients. And so you have different metadata. You can have multiple metadata servers. So in Expanse, we have 4, and we can have a lot of storage servers. So forget what the Expanse probably has 16, I think. So the thing is that your scalability comes from writing to these targets. So this is the exact Expanse architecture. So you have 12 petabytes raw and roughly 11 petabytes formatted. We get about 140 gigabytes per second and 200K on the IO operations per second. We do have the configuration to write data on metadata for small files. So basically, the small files can land on the NVMe instead of spinning disk. So we have 18 OSSs and 4 MDSs. So if you look at each of these servers, we have 16 cores, right, on the MDS. So keep that in mind, and 24 cores on the OSS. So as you can see, since we have 18 OSSs, and if you have a file that's being split over a lot of targets, you can get a lot of scaling in performance. That's how you get performance on Lustre. So like a client might request a file write, and the MDS can query and also do the file creation, and then you can actually write directly from the clients once you have the IO and path set up and have the info from the MDS. So that's what essentially happens. So the thing is, if you do large blocks of IO, that is like you write in big chunks, right, like megabytes, 1 megabyte chunks basically, then what will happen is this piece, which is querying the MDS, will take very little time, and then bulk of your time will be spent writing directly to the OSS. But if you make those chunks very small, then you will return the writes really quickly from each OSS, which means that then the metadata server will keep getting hammered more and more with more requests. And that's what happens with the small files. Now, Lustre by default, so there is a default Stripe for files on a Lustre. On Expanse, we've set it to 1 because we've kind of realized most users don't actually write big files based on our previous machines and data of the distribution of the data. But if you have a large file, you can actually split it up into a stripe count of n. You can pick this n. You can say, I want it striped over 8 targets. And you can say the size also, right? So it can be a 1 meg. So say you have a 10 meg file with a stripe count of 8 and a stripe size of 1 meg, you're going to have basically one stripe on each written out across each OSTs, each of the 8 OSTs, and then it will loop back and write on the first 2 to get to the 10. So that's how the file system writes out. So that's how the file is laid out on the disks. So each of these targets actually is comprised of I forget what the exact configuration is, but it could be like 10 disks, and you could probably get 600-700 megabytes per second from each target. So if you have 8 targets, you can see how it can scale up and get lots of performance out of it. And if I go back to my previous picture, basically we have 18 OSSs, and then on each OSS, I think we have like 6 targets. So you have a lot of storage targets to hit. And that's how you get to 140 gigabytes per second by basically splitting across. Which also means that if you want performance at large scale, you need to write in big blocks, and also B, stripe, because if you just do a default stripe of 1, then you're going to write to 1 target, and the target will be limited by the disks on that are behind the target. So if you want real performance at scale, you need to basically write out across. Now, if you write 64 files, for example, Lustre will automatically spread them across all the OSTs. So it'll round robin and kind of put each file on a different target. So you'll automatically get performance that way. So striping is good for storing large files, and also, because you can access the file in parallel, because each of these targets, the client can read from all of them simultaneously. So that kind of increases the bandwidth. There are some useful LFS commands. These are Lustre commands. So LFS help will give you options. OSTs gives you all the target list, MDTs, and Get Stripe gives you info on a particular file or directory. And Set Stripe can set the striping information. So if you set a stripe on a particular directory, say this directory is stripe 4 with a default with the stripe size of 1 meg, any file that's created in that directory will inherit those stripe parameters. So this is how you run it. LFS Get Stripe, then it will tell you the stripe count is 1, the stripe size is 1 meg. It also tells you the offset, which is useful if you're trying to figure out which target it's writing to. So if you see something running slow, maybe there's a target with a problem, you can go check it out. So again, these are more options. So there are other LFS commands like LFS quota. So if you want to find out your usage on a file system, use the LFS quota command. So here we walk through an example of making a directory, setting the stripe on the directory, then creating a file, and then do a get stripe on that. And you can see that the stripe count was inherited, so it got split. Now, if you have a few kilobyte sized file and you do a stripe count of 4, it's not going to be useful because you're basically wasting the other location. So because your stripe size, you just need one stripe count of 1 if for a small file like that. So when you're using Lustre, some things to keep in mind. As you can see from the picture before, the metadata servers are limited in number. There are 4 of them, and actually when you write to a particular file, you'll only be dealing with 1 of them. So unless you striped the metadata as well, but usually it's like 1 metadata server talking to a bunch of OSSs. Now, when you do an ls-l in a directory, it needs to find all the attributes of the files there, right? Including whether is an executable, when was it created, like all kinds of things. All of those are metadata operations. And if you put in color, it'll force metadata operations because it's going to try to find out more info about the file, which means you're going to hammer the metadata server. And since there are a limited number of those, and you go do this in a file, in a directory with say 1,000 files, now you just created a huge number of metadata requests just by that one command. And you'll see on a Lustre file system, if you do this in a directory with too many files, it'll slow down. And if enough people do it, it's going to slow down the file system for everyone because there's a queue on the metadata server. So, and I can show you that a little bit later. Similarly, don't do wildcards. Like, we often see people have like 10,000 files in a directory and then they do ls c star. Well, if there are 10,000 of those files, you pretty much did the same thing again, created a metadata load. That's the why of it. So typically we suggest doing bin ls because then that takes out any color options. And also try not to use tools that list the files in a location by default, like because if you do that in Lustre, then you're basically doing all these commands. It's a GUI, but it's doing the same thing on the back end. And also, don't use wildcards. Try to get as close as you can to the file system, file name. And if you're deleting like files in a directory, either do it programmatically so you don't do a wildcard, or we have a tool called dir scan, which can be used to basically delete files in Lustre. And then for your application itself, make sure you select the appropriate stripe count and size. Best case selection can be a bit complicated because it depends on how large your files are going to be, what's the IO access pattern, and so on. The other thing is don't store too many files in a directory. So definitely don't use a flat approach in the Scratch directory, for example. Like some users do this where they just keep putting more input files into the same location and then keep running jobs there and just keep piling up output input files in that location, and pretty soon they have 80,000 files in a directory, which is okay in an NFS directory, but even in an NFS it'll be slow, but on a Lustre file system it causes more problems because of the metadata issues. So at this point, I think I can do a small demo, but before I do that, I might just point you to the location and you can run this offline. You probably don't need to actually run this right now, but I can go over the output for you. So the demo is basically an IOR benchmark, which stands for interleaved or random I. So it was developed at Livermore. It's basically a good benchmark for test parallel file systems. Current version is pretty versatile. It lets you do lots of different options, types of IO like POSIX and MPI IO, HDF5 and NCMPI. And it controls lots of aspects of the IO so that you can mimic a real application. So you can control the overall IO size, you can control the transfer size, so the chunks that you're writing in. You can control whether you want to write a single file or write like a file per task, random IO, sequential IO. It has Lustre specific options. And also has GPFS specific hints, but that's a different file system that doesn't exist on Expanse, so you don't have to think about that. So IOR-H will give you all the options. Some important ones are here. Basically, -F makes it write one file per task. -B tells you the block size, that is how much each task will write. And then T is the transfer size. This is important because if you make it too small, then you'll be writing in small chunks, which will again increase the metadata load. Then you can also say only write the file or read an existing file, and you can control the number of iterations and the type of IO, for example. So if you want to run this demo, go to CM shared examples SDSC local Scratch. This is the examples directory, and you can just copy this local Scratch script along with the executables that are there. And Mary will go into running jobs a little bit more, so I won't go too much into the Slurm details here. Just remember that basically we are choosing a shared node. We are saying one node with 16 tasks. And this, I wanted to show you this script to kind of illustrate how you can use the local Scratch. So here what I'm doing is I'm actually copying the binary to the NVMe location. So I'm doing, this is the IR binary. I'm copying it to /scratch $user job _ $slurm _ job ID. Remember that this, you don't have to do this. I'm just doing this as an example. But if you have input files, you can copy them this way. Now, one thing to remember is when you run a copy command by itself, it's only going to run it serially on one task, right? So if you have multiple nodes and you want to copy, you actually have to explicitly do that on multiple nodes. But for now, single node, this is an easy way to show you what to do. So I'm copying this file, and then I'm changing to that local Scratch and running my benchmark. So I'm loading some modules and running the benchmark. IB_run is kind of an MPI launcher script that we wrote. And once this task is done, there's an output file. I'm redirecting all the output to this output file. And I'm saying I'm going to copy this output file out. Remember, this location, this /scratch $user will get purged as soon as it reaches the end of the script. So if I don't have this copy flag, then that output would get deleted. So I'm copying it back, basically. So this is loosely like a workflow for using local Scratch. And when it runs, you'll see there's a lot of output in that file, but eventually the IR output will say what kind of API it was using. So I was doing POSIX, and then I was doing file per process. So we're going to have 16 files written out. And then read back in the benchmark. And it's just a sequential offsetting. And then I'm doing just one iteration, transfer size of 1 meg and a block size of 1 gig. So it's writing 1 gigabyte from each task. So you get a total of 16 gigabytes. That's the benchmark, basically. And you get, some decent performance out of it, around 4 gigabytes per second. There's a little bit of caching in this, so it's not the real number, but kind of a good close estimate, I think, of what you can get out of that NVMe. So at this point, I'm going to kind of go through some scenarios, right? So if your application wants to write a checkpoint dump from memory for a large parallel file system, so where would you stick this? Maybe, I don't know if I should ask people to put answers in the chat, but I'll just give it a few seconds and then give you the answer, I think. For a situation like this, it's a large parallel simulation and you're doing a checkpoint dump, it's best to write it out into the Lustre parallel file system. But as I mentioned, it's good to use IO libraries that are optimized for these things. So like an HDF5 is a good example of that, because that will write optimally to Lustre, which then eventually means that the Lustre file system load will be low. So next use case. So you want to write and read thousands of small files local to each process. And you want to store files across all these processes. So what would you do with that? And you might know the answer to this. Basically write to the local Scratch, but then copy out what you need to Lustre. The last one I have is a workflow requirement. Say you have a workflow that runs thousands of jobs, each of which writes and reads, say about 10 files each. So, but they've been written continuously. Now, if it's a small job, like say it's a job that only needs one task, one core, you might run all 1,000 of them simultaneously. And this has happened. This is a real scenario that I'm presenting. I'm going to show you what happens to a Lustre file system when you do this. So what this would do is basically 10,000 writes continuously throughout the job, right? Jobs, right? Because it's combined together. And this is perfect scenario where you should be writing to node local NVMe, because if the job is small, it's going to fit in the NVMe, and also and if it's a single core, you can scale pretty well. Even if you have multiple jobs running on the same NVMe, it should be able to handle. And then only copy out results to the Lustre file system. And I want to add one more thing here. If your job, say, creates 10,000 files and you need all 10,000 files, don't do a copy of all 10,000 files with like a wildcard from NVMe to Lustre. That's going to create the problem again. In such a case, what we say is make a tar file. So you can just directly tar up all 10,000 files into Lustre, right? So you would have a single large tar file in Lustre. So why do we care about this? Well, this is an example of a IOPS load from a very ill-designed IO workflow, where the user essentially did what I mentioned before. Thousands of jobs with tens of files being written from each job continuously, right? So you can see on the Lustre file system, we have some monitoring internal to SDSC where we can look at it and could see about 8,000 files per second being created by this one user. The rest of the world is down there. Like you can see these little colored lines there. That's all the other users. And this was this one user who had thousands of jobs. And this drop is because we spotted it and stopped the jobs, because if this is continued long enough, it can cause severe problems on the Lustre file system. And why is that? Remember, each of the MDSs had 16 cores, right? So typically the load on these MDSs, MDSs that can deal with the, load of about 20, 30 is okay, right? So you can see this was going pretty fine until somebody did something crazy and you ended up with a load of 338 on one of the MDSs. If you go look at the corresponding OSS load, you can see there's actually a drop off in the writes there. And if you actually go look at the MDS operations, there's actually a blank in that time period. Oops, sorry. What happened is basically the load's at 300 and the file system is basically busy responding to just the requests, and it's piling up. So it doesn't even have time to do the IO. The server doesn't have the cycles to do the IO properly. So the IO pretty much drops off to almost zero. And if this continues forever, like if people just keep piling up on that, at some point the server will crash because the load is going to get too high and things will start timing out and so on. So it's really critical to avoid this kind of workflow. So I think I saw a question there that says, is there a middle layer that detects problematic IO patterns from users? So the problem is these are coming from different jobs. So you really cannot condense them. If it's a single job, you can do something like that. Even that needs a special hardware setup and so on. I think one of the systems on Xseed has a burst buffer, which would do something like that, where you have lots of IO going into the buffer, and then that that gets written out. But that doesn't take care of the metadata problem, because that only can take care of the IO side of it. Like that is, like if you opened a file and wrote lots of little pieces, you can condense all those little pieces into a larger write and then write out the larger write. That works okay. But what's happening here is every time you do this, the metadata has to update with the little piece that you're writing, because it has to keep track of what's going on with the file, right? Now, the problem with that is then that's a request to the metadata, and having a buffer is not going to change the fact that you still need to go to the metadata server. And in fact, in those cases, the buffer makes it worse, because now you have piled up things hitting the metadata server. So, yeah, that's a partial solution, is what I would say. There are other kinds of things people do. They relax some of the POSIX requirements. I think the new machine that's coming up at NCSA, trying to remember the name, but basically that machine is going to have a file system with that kind of setup. Now, remember, that's a pretty interesting choice, and will be interesting to see how I/O gets handled. It should do better in this kind of scenario. But then the flip side of that is that the user's application needs to be able to handle that kind of I/O and not have wrong answers because it can't deal with it, right? So there are both sides to every solution usually. But the key thing to remember, to take away, is that this is something you should always be thinking about. Like, what is my application doing with the I/O, and how many of these instances am I running, right? Like, am I doing 10,000 of these? Oh, then it's a problem. But if I'm running 5 of these, it's not a problem. Like, if you have 5 jobs running, writing out 10 files each continuously, it's not going to do anything. It's going to be fine. So I really need to think about your I/O pattern and then make a choice. It is important in all stages, before, during, and after simulations. We've had users cause problems just with the moving data in part of it, because they do metadata intensive movement, and then that causes problems. And like I said, the poor I/O choice can affect everybody. Like, you saw that metadata server was not responding for like a little period when the load spiked to 300. That means no one on the system can access the file system at that point, or it's going to be really slow. You might do an LS and come back after 5 minutes. So that choice affects everyone. So keep that in mind. And data provenance and integrity, they're important considerations. And I talked about the open science chain tool. And I think I saw Subha join. So if you have questions about that, you can pop one in there. We saw all the options available on Expanse: node local NVMe that can do high IOPS, large Lustre parallel file system that can handle large block IO. Choose the right one depending on what you're doing. And the last point is, please have offsite copies of anything critical. Do not depend on a file system for your only copy, because these are dynamic file systems with spinning disks, and spinning disk can fail. There is redundancy, but you don't want to be depending on that. Always have multiple backups of anything critical, especially code. Like, if you have code, I would say check it into GitHub or someplace where you can retrieve it and not depend on a live file system for your only copy. So back up anything important, and that's what I would leave you with. And any more questions? I think I'm 3 minutes over. Let me take a quick peek at the chat. Looks like that was the last one.
Okay. All right. Okay, so let's get rolling. One of the things I wanted to take a brief moment for is we do have the training repository that I think Cindy has put in there a couple of times, and we're starting to add in the weeks as people speak. We try to populate the repository with information and relevant material. For example, for Bob's, there's a link to his repo, and he's got a Jupyter notebook in there that we'd like you to try and run some small activities like that. And just knowing where these are, you can clone the repository if you want. And for example, my talk today, I will get our links to our talks, and then any small examples that we might like you to run. Like, I'll have a code that you can run today and submit to the batch queue, and I'm sure Mahi has a couple. If you are going for a co-curricular record credit, if you're a student, or if you want to get a certificate, then you need to finish some of the work and put it in a reporting format that we can track. So I also uploaded a document that describes that. It really is just a naming convention. So my checking scripts can go in and look and see if and verify that you've been doing some work. So that's about it for the repo, but I am getting that populated. Okay, so let's go ahead and start with our first talk. I broke my presentation into two talks. One is on basic concepts of accessing Expanse, and then the other one is the basic idea behind running jobs and using the batch queue. So let's get started on that. And again, I will try and not take too much time. So we'll just do an overview of Expanse, look at basic skills. I want to mention that. Usually when we do a large workshop, we take a day called a prep day, and we go over some of the basic things you need to know. And if you don't know them, you might want to learn them in order to use Expanse effectively and other HPC systems. A brief hello, this is Expanse. I'm just double typing that. Logging on, running modules, and account management. Some relevant links to the user guide, Bob's overview. You need an account, and most of you already have an account. You should have one. If not, check your portal account and make sure you can log on. There were some account issues that will get in touch with these people, but you should all be able to get on and say hello to Expanse. So this is a picture of Expanse. It's in my background. You can see it. It's a big machine with lots of colorful lights in there that illuminate the fact that it's liquid cooled. These are called the racks, or the scalable compute units. Bob talked about that the other day. But I realize you guys probably don't know what it looks like because we can't go in and do a real tour. Hopefully in the next few months, they'll open it up so we can start doing community tours, and we'll be happy to arrange one for you guys. It's quite exciting to go in there and be physically close to these big, loud motors running, and cooling fans are blowing, and it's quite interesting also to just see the hardware. So I use that as my background this week. As Bob pointed out the other day, just to remind you, Expanse is a very big system with these what we call scalable compute units. Each one of those racks that you see illuminated is an SCCU. It's got compute nodes, GPU nodes, and high-speed network interconnecting it. And then we have all these high-speed networks, as Mahi just pointed out to you. Advanced features of Expanse allow you to do things out on the edge and do edge computing and remote computing. It's an interesting machine. This is that diagram just to remind you that scalable compute unit, one of these tall guys behind me, a rack, has all these features on it. And when you get onto Expanse, you don't log right onto one of these scalable compute units, and I'll talk about that in a moment. But you do have access to all this storage, and it is important to be aware of how you're manipulating and moving files. We've noticed a lot of file I/O increase with the adoption of machine learning and deep learning. So we know that it's going to occur, and we just want to help you guys do it more efficiently. One way to get on is to log on to Expanse. I'll talk about that. There is another one, which is to log on to the Expanse portal, portal.expanse.sdsc.edu. You can log on, launch jobs, run Jupyter notebooks, run R, MATLAB, and it sort of reduces the pain of getting on and running some applications. So feel free to explore the portal as well. I won't go into that in any more detail. So what do you need to know to work effectively on Expanse? You want to have some basic skills. You need to know Linux. You need to be able to understand what SSH is, so what's security and authentication. You do need to understand GitHub repositories. Most people do, but if not, we have in this basic skills repo, we have many tutorials on running GitHub, for example, using it on Expanse. Then you can go out and find a lot of online tutorials. The same thing with Linux. We have some examples of how to do things on Expanse, things that work with real examples from a file where you can cut and paste and try the examples yourself. And then a goal of my talk today will be to help you understand the environment that you're working in. because that can be more frustrating than any aspect of trying to run your job on an HPC system. So logging on, you have to get onto the machine. We use single sign-on authentication. You can log in from the command line or the portal. And to log into Expanse, you use an application called Secure Shell from a terminal. And both Windows and Mac systems and workstations, they all have terminals where you can type this in. This is the domain name for the login node. You will have a username on that machine, and you would type SSH username at login.expanse or pass that, use the -L for the username there. And I'll show you an example. You can authorize different ways of authenticating on Expanse, and one is to create an authorized keys file to allow you to do access without directly entering a password every time. And that's using something called SSH agent. And in our basic skills repository, we have an example and instructions on how to do that for Expanse. And it depends on the fact that you own the laptop that you're on, you have an account on Expanse, you have a username and a password, and because you have that username and password, you're allowed to copy files over there and put them where you want with authentication. And once you can get some authentication credentials copied over to Expanse, then you're allowed to go from your laptop, for example, directly over to Expanse. So again, we have more information, and there's some great tutorials out there about SSH agent. And Scott Sakai will be giving a tutorial in a couple of months in our webinar series that will go into all of this in a lot more depth. We do have a presentation that he gave last year on Comet, but it also applies to Expanse. If you're logging on, what's happening? There's these big boxes behind me that are all lit up, and those are called the compute nodes, or racks with a bunch of compute nodes in them. You're a person and you're trying to get into them, so you log into what we call the head node and the scheduler system. And the head node is where we call that the login node. That's where you work most of the time. When you want to run a job, you submit a job through a scheduler system, and we'll talk about that in the next section of this talk. You would submit a job, and the scheduler will decide which of these nodes would be needed and useful for your job, and set you up so you can run a job on these nodes. Imagine, 5,000 people logged on to Expanse, and they're all saying, I want node 1. No, I want node 1. Well, that doesn't work. It's not very scalable. So we have scheduler software that we work with. Ours is called Slurm, and I'll talk about that. Okay, so that's getting on and logging on. And when you're on there, you get some kind of greeting message that should say Expanse. It looks kind of messy in the image, but you'll get what we call the message of the day, and that way you'll know you're in. And it will tell you the last time you logged on. If that doesn't sync with your memory of the last time you logged on, please let us know, because maybe you've been hacked. You have to be careful with your passwords, and people are trying all the time to hack our systems. The login nodes have a special use. They're meant for file editing, data analysis, and small tasks that don't require a lot of compute power. Don't launch a job. You can't even run MPI on the login node. Computationally demanding jobs need to be submitted and run through the batch queuing system. Don't use them for computationally intensive processes, for long-running workflow management, primary data transfer nodes. We have special ways to transfer data, as Mahi described. Don't use them as servers for other services or for running Jupyter notebooks. Well, I'll show you very briefly today how to get what we call an interactive node if you want to work directly on a compute node and compile and debug your code. But we'll have a whole session on that in a couple of weeks. We'll go into more in depth. So they're not the same as the batch nodes. They're smaller memory, and a lot of other people are on them. Again, this is the kinds of things you can do in the portal, a reminder of that. So that gets us on to Expanse. And then you want to understand something about your environment. If you don't understand logging on, SSH, environment variables, then you really do need to go back to the basic skills of Linux and work through my tutorial, which is written in Markdown, and it's made so you can cut and paste to figure out what's a file, where things are, change directories, things like that. If you've already done that, then you should be comfortable in that space. Expanse uses an environment control system called LMOD and controls your environment through modules. When you log on, you have a certain environment, and I'll show you a demo when we do some login examples. And who are you? What folder? What files are you on? What files are in the directory that you're on? What date were they made? All this information is part of your Unix environment. And what your task you're trying to do, are you trying to run an application like Games or Amber? Are you trying to compile a code, even Hello World? What compilers do you need? What language are you going to work with? All of these need to be defined in your environment. And the older way of doing that was everything was installed and available to you, and you had to fish around and find it and use the right paths and set all that up. Now what we do is if you want to load a Fortran compiler, you find the module with the kind of Fortran compiler that you want, or a C compiler. Do you want Intel? Do you want some other library from another compiler manufacturer? You can pick and choose what you want for your application, so you can customize your environment and have it the same way every time you want to work in the workspace that you're currently in. And it's beyond just being in the right folder or directory. You have to define the environment, the shell environment variables that you want to work with. And it's dynamically modifiable too. Very powerful, a little tricky to get to know and learn about at the beginning, but once you get it, it's not so mystical. So you do need to make sure you can see the Slurm scheduler, and you don't see all the available modules when you run module available without loading like a compiler. You can't see what compilers are there. And so you want to find out what modules you've got. I'll show you some examples of these commands. If you can't find what you're looking for, you can use the spider command, module spider, some package that you want to know about, or using some keywords, and then you can start finding what's out there and start loading the packages. Once you load a package, then you'll get more information about the related modules that work with that package. So you have to know where to start, and that can be frustrating. If you have trouble, contact the help desk and they'll help you figure that out. But once you do, keep track of the modules, and we usually keep a list of them in a text file. And then for more details on an application, you use module spider. The module paths are different for CPU and GPU. So make sure if you're on CPU, you want to load this module called CPU. And if you're on a GPU, load the GPU module, don't load both. And when you go onto the GPU from the CPU, you start with a fresh environment. So you'll have to reload your modules. Here are some of the more common commands. List the modules that are currently loaded, which ones are available in the environment that you've got. Spider, display information about the module. Unload and load a module, get rid of one you don't want, and load the one that you want. You can use something called purge to get rid of all the modules and just start over. You can swap, for example, a different version of a compiler, like the Intel compiler, version 19 and version 20 or something like that. And you can get help, and there are shorthand notations. So here's an example on Expanse. Expanse has 2 login nodes, so you might log into login 02, and you might log into login node 01. So you might see this change a little bit. It's the same machine, it's just a load balancing. And we want to reset the modules to the system default. And here I'm listing what did I find in my current environment. I'm on a CPU, I'm running Slurm for Expanse version 20.02.3, and I have the Intel compiler loaded in version 19.1.1.217. And then what modules are available, because I have these 3 packages. I have a lot. This is often longer than what you're seeing. I have Spec, I have Jasper, GCC compiler, Parallel. So I have a lot of options for different packages. And if that isn't working for you, then you want to look and do Spider for the package that you want to find. Use module show to find out what a particular module has defined in it. And sometimes this is really, really long. CMake is a short description here, but there can be a lot more information. It does show you, I'll point out, where CMake and where it lives. So we know we're in this SPAC directory. So I'm going to load the GNU compiler, and I'm going to have it show me information about the GNU compiler, just a little bit less information here. So command not found. Sometimes when you're switching around a lot and changing modules and going in and out of being on a GPU and on a CPU, in and out of the interactive mode, things can get a little confused. And so you can just sort of reset everything by running this source etc profile.d module shell, or just add it to your shell script. So whenever you're logging into a new system, you just start over and fresh. Last topic in this is your accounts. So you might have access to multiple accounts and different projects. And so you'll want to know which account, which project are you working on, and what are you charging to. And you should verify that you're using the correct project in the batch job. You can't run a job on Expanse if you aren't allocated and on a project that has granted you permission. Like you're all on the HPC user training allocation. And there's a limit, we've set a limit on everybody. And so don't use up your limit. So you can look for that by running an information command, which I'll show you in a moment. So the projects are very precious. The allocations on Expanse are very, very, very precious. And so don't abuse the allocations, or whoever is your PI or allocation manager, they might just cut you off if you use up all their allocations. Things happen by accident, and when a problem does occur, be sure to let us know. Okay, so in the batch script, and I'll show you more about that, you would define it using sbatch-a, or as an argument -account equals, and this would be the project ID, project number. Here's an example. To figure out what projects you're on, we have a command called Expanse Client User, and that's in the SDSC module. So you have to remember to load that in, and then you'll be able to run it. And this one just tells me all the projects I'm on, and sometime whenever I ran this, this is how much I've used and how much is available in the project overall. ABC123 is just a cartoon example in my examples I show you guys. It doesn't really have any allocation that really works. This one is looking for what do I have on Expanse GPU. Charge unit for all the SDSC machines. So how do we charge? It kind of depends on what you're doing. The basic dollar metric on Expanse is the service unit, and that's defined. Here it's 1 CPU core using less than 2 gigs of data in an hour. And the shared partitions, you can share a node with other users and pay less. If you grab a whole node and you don't share it, then you'll get charged for that at least 1 hour for that whole node. So be careful how you're using it. The minimum charge for any job is 1 SU. And I advise you to go look at the Expanse user guide, which has the most current information about charging on Expanse and all the material in these talks. They update that continuously, and it's going to depend on what job how long you run your job, what queuing partition you pick, and I'll talk about that in the next presentation, I think. Okay, so that's it for this short overview of accessing Expanse, and I'll go to the second talk, but first I wanted to show you very quickly what it looks like when you log on to Expanse. So can you guys see the font here pretty well? Is that big enough? Or do we need to go a little bigger?
A little bigger.
Okay. All right, so I like to alias commands. And so I'll just go ahead and use the full command SSH-Y so I can do exterminal forwarding. There's my user ID, M. Thomas, and there's the IP address. So when I log on, there we go, I'm on Expanse, and I can say who's on the machine. A lot of people are on the machine. And so I can do, where am I? I'm in my home directory, who am I? All of these commands are in that markdown file, basic Linux skills in that basic repository. So we'll come back to this later on. I won't take the time to do all the live demos until I finish this presentation, so I can make sure we get through it. All right, let me get the running. All right, so what do we need to know to be able to run a job on Expanse? You already know that you have to get files onto Expanse and move data around. So the focus of this talk is to just look at, you know, like I said, how to run jobs. And there's a core part of it for some people, which is compiling and linking code. I won't dwell on that today because our focus on this talk is just getting in there and running jobs. And if you're going to be compiling, developing, and linking code for development work, we have session 2, which focuses on parallel programming of code and the parallelization using MPI and OpenMP. But you still might have to come in and take code that's already there, make a little change and compile it and link it. So I'll talk about that very briefly, and then talk about the Slurm compiler for running jobs and an example. And then I have some additional examples that are just included for completeness. Okay, again, some useful links. There's Expanse, and I'll skip through this because we just covered all of that. And get to compiling. If you've done any kind of programming at all, you'll know that there's commands you have to use to build. You might be one of the users who is just going to work with something that's already compiled, and all you have to do is, for example, fix some input files and make sure you've got all that characterized properly, and then you modify a batch script and it reads your input file and off you go, like games or Amber. But if you have to compile, then you need to know that there's a difference between CPU and GPU compiling, and we support a large, broad number of compilers, GNU, Intel, AMD. We have MPI implementations, OpenMP, MVA Pitch, and Intel MPI. And a lot of our code has been built using the GNU compiler, GCC, and special flags, and we get excellent performance. So the compiler, you may want to be testing different compilers because you can get different performances depending on your code and the system that you're on. And also we have extensions for advanced vector computing. And for GPU, we have GNU, Intel, and GPU. And the Expanse login nodes and the GPU nodes, to get onto a GPU, you would log in onto Expanse and then get on a GPU. They're different. So you have to be aware that those compilers are different, and of course you compile your code differently. In the user guide, you'll find a template for all the different compilers. Here they specify 3 languages, Fortran C and C++, but there are other languages, like we support Python and other languages, but the examples in the user guide focus on these 3 primary. Java. So there's a serial command for compiling, an MPI, OpenMP, which is a threaded process, and then hybrid for MPI and OpenMP, for example. And so you have to know which modules, and in the user guide, we guide you for the basics, like for this compiler, you have to load AOCC, and then you can also get help. So here's an example of using that compiler. I currently had all of these modules loaded, and I didn't want them to interfere with my ability to compile with the AOCC. So I list no modules. Then I'm going to load Slurm so I can run jobs on the Slurm queuing system. I'm on the CPU device. I want to use the AOCC compiler. I also want to do MPI, and now I have a different suite of modules. So the purge command is very powerful. It just cleans everything out, and then you can start over. And again, this is like a little recipe for your environment, basic things that you might always need. And then as you get more customized. And in our help, we have example code that you can download, and I'll show you the link to the tutorial. And we have README files that contain the module recipe, and we also advise you to put them into your batch scripts for running the jobs. Okay, so that's just a little example of how to change the modules using modules. There's Intel compilers, and here are the commands for that. I'm going to skip through there. There are examples here for you to refer to. There is the Intel Math Kernel Library, which are excellent if you can work with them. And we do have an example for just some basic matrix multiplication, and another example for you to use for the accessing the Intel Math Kernel libraries. Here we have the Portland group. This would be on the GPUs, and Portland supports, PGI supports a lot of different languages and environments. For GNU compilers, there's the example here, and again, GNU is open source. It's really popular, and you can get very good performance. One thing that if you're working on different machines, it's important to be able to port your code. And so portability is important, and GCC is everywhere. It's going to be on your laptop. It's going to be on your workstations and in the lab or at work. So it's not bad trying to work with a simpler compiler like this. You may have to change to other ones though. And there again, they're setting up the environment. So running jobs. There's this concept of where is my data, where's the memory, where is my job being run? And this is what we call the distributed memory model, where you have all these individual compute nodes. They're not connected except through this interconnection network. And so for this CPU 0 to exchange data with the last CPU, they have to send a message along this interconnection network. And that can be expensive. What we try to do is build up like our scalable compute units, network nodes that are very, very close to each other, nodes with a lot of cores. There are 128 cores per node. And then that more work can get done on that one node. But at some point you have to, for really, really big jobs, send messages. And we'll talk about that in session 2. The shared memory, these CPUs all share the memory, like 128 cores on a node. They have local, what we call shared memory, real high-speed interconnection. I'm going to move through this. So when you're running a job on Expanse, you run jobs in the batch mode. That means you're going to submit the jobs to the batch server. The batch server will take care of your job for you. You just have to give it working code and a good batch script, SBatch, the commands that are in the script. And that's where we run computationally expensive jobs. Batch jobs, submit to the Slurm server, and I'll describe that in a moment. You have to know what partition you want to run on. Partitions they have different policies for how long you can run a job, how many SUs you get charged. There's different time limits. There's a limit on Expanse of 48-hour jobs. If you have something longer, you can request more permission, more time. And you have to know the number of nodes, the task per node you want to run. If you have 128 cores on a node and you only need 24, you don't need to ask for all 128. You could share it. So you would just do 24 tasks on that one node. You may need to describe your memory requirements as well. You need to know your job name, where you want your data to go, and you may want to have information emailed to you so you can track your job. We use the simple Linux utility for resource management, Slurm. Yes, they chose that name on purpose. And you can, so there's batch jobs and then there's interactive jobs. So these are the two kinds of jobs you can use. Interactive job is when you launch a command and ask for an interactive node, and then the system will log you onto it automatically. And you would say, I need that node for 30 minutes. And for 30 minutes, you'll actually be on that node by yourself, and you can run and test and compile and debug, but just be aware that you'll have a time limit. And I think our limit is 2 hours right now. But it's a great way to do interactive computing. You can do it on the CPU and the GPU. Note in my examples, that's a fake account number. You have to use something real. And be careful, if you ask for 2 hours and you walk away and forget, you're going to get charged for 2 hours. And you each have 500 hours in this class. So use your hours wisely. Okay, so the Slurm is a server. And again, here's the login nodes. There's the head node that you logged into. You're sitting here as a client, and the Slurm sort of helps to figure out which of these nodes are you going to have, and assigns them to your job. It has a lot of services that you'll interact with. SQ is how are my jobs running. SBatch is submitting it. It does a lot of work, and it's the reason parallel computing is as efficient and effective as it is. This is a list of what we call the partitions. We define the partitions to be compute or shared for the CPU or the GPU, large memory. There's a debug queue, which is 30-minute limit. Maximum number of nodes is 2, but it's a great quick turnaround for you to test your code. So make sure when you're doing testing and then going into running jobs, you know what queue you're in, what partition you're picking. So to submit jobs, the common commands from Slurm are you want to submit a job and get it running. You want to check your job. Is it still running? Does it have any problems when it's done? Or while it's running, you can monitor it. And also you can cancel a job. So SBatch is the command to submit, and that's the name of what we call the batch script. Again, if you're familiar with Unix, you know that you can do batch script code, and that will execute a sequence of Unixy commands. Slurm and all the queuing systems, they have their own batch script system. It's basically a Unix batch script, a Unix script with special commands and definitions, variable definitions, and a special environment that the Slurm server knows how to process. And I'll show you that in a moment. When you submit a job, you'll get confirmation that it worked or an error code. There's your job ID, 8718049, and you can check how are the jobs running for me. And here I say I have one job running and it's pending. Once it's running, I can keep an eye on how long it's running, how much time it's taking, and I even know what Expanse node it's running on. I can kill a job by using the scancel command. In Slurm, there's environment variables, and you'll use them a lot. And I put in here these 2 links that give you all the environment variables for what they call input and output. For example, when I want to give the job a name, I can use that variable and define it in my script. If I want to know the job ID inside my script, I can call and I can use this variable inside my script to get my job ID. I could even pass that to my code. So there's a lot of power in knowing how to use these environment variables. I don't have time to go through all the examples, but you use quite a few of them in building the batch script, and I'll point that out to you. So here's an example of the sample code I'm working with today is computing prime. It's really very simple. I've got the code. You don't even have to compile it. I'll have it all uploaded on the repo and available on Expanse. But basically inside the Slurm, we tend to use some kind of dot extension, and this is SB for Slurm batch. You can call it what you want, but typically the application and then some extension you recognize that this is a batch script for running jobs. I use the bash environment, and then these #SBatch, these are keywords that are recognized by the Slurm server that, okay, I need to process anything that has SBatch in it. A job name, I defined it to be MPI_prime. I want the output to be MPI_prime %J %N. And that gives me the job ID and the job name in the output. So I'm controlling the name of my output file and where it's going. Mine's by default going to go in the directory where I submitted the batch script. The partition here is compute or debug, and I've got that commented out. So I'm actually using the debug, just one node, only 24 cores, and the time 10 minutes, and there's my account. Don't use that when you're not on it, so don't use it. And then here I'm loading in that environment with the same modules I used when I compiled the code. And I'm going to echo some information so we can see that indeed these environments work. And something key to realize is that inside this batch script it's a Unix script, so you can run any other Unix commands that you like. Here I'm just showing you how to get the date and print it out. And there's the command to run my MPI prime code. And then here's the sbatch command. I'm sneaking in a little feature here, which is passing a variable into my script. In this example, I'm not using it, but in the next example, I'll show you. So I've submitted my job. I got a batch job 9113467, and there it is in the partition, and it's running. And then I got some output where you can see that I got some prime numbers between 1 and 262,144. I'm doing well on, how am I doing on time? Okay, I'm wrapping this up. So you can pass variables into a Slurm job. This is a really key feature for doing scaling, parameter scaling, for example. So you use the -- export equals, and then x equals 7 and b equals my string. Or you can use the export equals all, which will load them into the environment. I had a link to, in this slide back up here, the Slurm schedule, md.com, sbatch.html, that will tell you all of the information that I showed you here, and also for exporting, for importing variables. So in my code here, I am passing in a variable called nlow, and there's a typo. This should be MPI prime with nlow passed as a variable. So I can use the value that I'm passing. And here I'm setting nlow equal to 1000. So let's see, very quickly, I want to go over the interactive computing. Again, we'll have a whole session on this, and that's when you get software that interactive computing is pretty generally whatever. I'm doing interactive computing right now from a computer science perspective. I'm interacting with an application, many applications. I've got Zoom, I've got PowerPoint in the background, I've got mail, I've got 15 different applications running, and I'm interacting with all of them. In high performance computing, since everything's running on the batch, on the nodes, you don't really interact with your code. So an emerging area of development in high performance computing and cyber infrastructure is, how do we support interactive computing? For example, to visualize and interact with data, when you've generated a petabyte of data, how do you visualize that? Well, it needs high performance computing resources as well. And so HPC computing, we need real-time interactions with our application and our data. Jupyter notebooks running on a high performance computing, that's a very popular interactive mode. MATLAB runs on HPC resources, and so does RStudio. So it's becoming more and more popular, and we'll have more sessions on that later on in the next couple of weeks. So to get an interactive node, there's an example in my talk. I'm waiting. I submitted a request using srun. Finally I get onto, you'll see my node ID has changed, and I'm on a compute node. Woohoo! And so now I can start running parallel code using different arguments to the srun command, for example. And I had a different module environment from when I started. And you can do the same thing on the GPU node. You can log directly onto the GPU node. And the way you can tell is if you run this NVIDIA-SMI command, it'll tell you that it's on an actual NVIDIA device. And we'll do more GPU CUDA programming in session 2. So the rest of this is some additional examples that I've got, and you can get those from the Expanse 101. Those mainly have just hello world, but it's a way for you to test compiling and experimenting and exploring the Expanse environment. And I'll be adding the calc prime to this repository as well. So there's just some general commands here for getting, like a recipe. Go to the directory where you want to run your code. Make sure you have the right modules listed. Compile your code properly. Make sure it's there, and then submit your job. And so that's all in this examples here. I see we're kind of running out of time, so GPU works about the same. The login nodes are not the same, so you have to make sure you get onto an interactive GPU node and go into a working directory where we have a Laplace example. All of these examples are in my tutorial and easily available. One of the things is for all of our examples, we have a README. We try to include a README file with some guidance, like for this example, you get some weird output, just ignore it. But in the README file, we'll tell you what module environment you need, the compile command, and then the command for launching. It's all very similar, whether it's on CPU or GPU. You should at the very least be able to take the hello world example and get it running on GPU. And it's a very quick overview of running jobs and doing things on Expanse. And thank you for your time. I have a link here to a training guide called Expanse 101, which has all of these examples in it. And you can go down and find the code exactly down here in the running jobs, CPU and GPU. So if you follow those, you should be able to successfully run jobs. And thank you for your time, and thanks for hanging around on a Friday afternoon. I appreciate it, and I hope this is helpful.